I would like to describe a field in which little has been done, but in which an enormous amount can be done. This field is not quite the same as the others in that it will tell us little of fundamental physics, but it will tell us much about the strange phenomena that occur just below our perception. In contrast to the natural philosophers of the past, the scientists of this field delve into the recesses of nature and show how she works in her hiding places. Their quest is to understand and create the imperceptible. After all, there is plenty of room at the bottom.
Hey everybody, welcome to the Materialism podcast, an exploration of the past, present, and future of material science and engineering. I'm your co-host, Andrew Falkowski, and I'm joined by Dr. Taylor Sparks for a special episode.
I'm psyched to be here. I've been traveling for a month, so thanks for taking the wheel and covering the episode for me last month, guys.
Yeah, it was a lot of fun.
We are here to talk about something which you have all seen and loved and probably wondered how it worked. It's that magic of things that glow in the dark, right? Andrew, did you have one of those little sets of stars you put on your roof when you were a kid?
I did, of course.
I would do it now, but my wife wouldn't let me. Those things are awesome, but what do they glow for, like 5 minutes, 20 minutes? By the time you fall asleep, they're getting dim. What if you could have something that stayed glowing all night long, right? In fact, I've got a company where we are making glow-in-the-dark roadway markings, like road paint. So instead of necessarily lighting up the road with streetlights, what if the light could just come from the paint itself? Yeah, the big difference between the glow-in-the-dark stars that only last a little bit and the ones that last a very long time, hours, is actually these are ceramic materials. And we love ceramics, and the American Ceramic Society is actually a sponsor of our podcast. And you're going to learn more about them if you stay tuned. We've got some really cool things to offer.
And it's not only ceramics too. There's plenty of organic molecules that also fluoresce, and you'll find these all throughout nature as well. In fact, in doing research for this episode, I came across a crazy article about biofluorescence in the platypus, which was never known before.
What?
And at first I thought, okay, maybe it's something they're swimming in, but no, they tested it across various samples in
Platypus
different
itself.
regions. The platypus itself under UV light will fluoresce.
So rad. So unexpected.
It's in the hair.
So today, if you've seen these things that glow in the dark, you may not have realized that there's actually two different categories. Actually, there's more than two, but there's two main ones we're going to talk about today. There's fluorescence and there's phosphorescence. Sometimes we use these terms interchangeably, but they're not exactly the same. And you've probably heard some of these terms before, like fluorescent lighting. Andrew, you've probably got fluorescent lighting in your house. I know I do.
Nope.
How do those work? You don't have any. You're like an incandescent or die guy.
Yeah.
What?
I get a headache under fluorescent lights.
Yeah. Okay. The color profile is different. I like the ones that you can set the sort of warmth of the light coming off of them now. Even that, though, it's not for you.
No, if I had my way, it would be candles.
Andrew would live in the woods making his own beeswax candles. All right. I love it. But for the rest of you, you've probably got fluorescent lighting. Ever seen those big long tubes? Of course you have. Inside of them, it's actually mercury, right?
Mm-hmm.
And the mercury is actually it's getting excited by the, applied electricity to this thing. And that is causing a UV emission. And then those UV light that's coming off of those is actually hitting your phosphors. No.
Yes.
Oh,
it's
they're
confusing.
phosphors.
They call them, the lighting industry has called them phosphors, but they are actually fluorescing. They are not phosphorescing.
Interesting, because I knew they were called phosphors, but I knew it was fluorescent. Oh, interesting. But anyways, it's not even the mercury. The mercury is exciting the things that you are seeing. They're giving off the light that we now enjoy and light up our homes.
That's right. It's a coating of multiple different fluorescent materials so that the combination of them will achieve a specific light temperature.
Okay, well, we got to explain people how this all works. And to do that, we've done our research for you, and we're going to get you up to speed. But we have to start with some basics of orbital energy stuff, because it's important for everything else that follows. And I know you've seen this before. If you've taken a Gen Chem course, you learned about, the quantum numbers like NLMS, and these describe different things, right? The distance from the nucleus, the shape of the electron orbital, the orientation, the spin. Those things are all super important. But also, we need to care about how these orbitals get filled with electrons. Andrew, help us out.
Yeah, you might also remember Hund's rule, which states that in a given electron subshell, every orbital has to be singly occupied before any orbital is going to be doubly occupied.
They're just like us. They also don't want to sit by each other if they don't have to.
That's right. Yeah, electron repulsion has an energy penalty associated with it. So if you think about a p orbital, right, there's 3 subshells that can be occupied. And when you're doing your diagrams where you're drawing those arrows that occupy those boxes or lines, right, you start with 1, 2, 3 first, and then you go back and you double up.
And when you double up, then we introduce this concept of spin. And we know that electrons can have spin, and that for them to occupy the same orbital, they have to be different spins. You can't put two of the same spin in the same orbital, okay? That lets us actually calculate something called spin multiplicity. Essentially, what you're doing is you're saying in the orbital, what's the total number of unpaired spins, right? And you take 2 times s, this total spin quantum number, plus 1. You probably saw this. You probably did this in Gen Chem and never thought of it again. But it's actually kind of slick, right? For example, if you have a single orbital where these things are paired up, so you got one up, one down, there's no net spin. So 2 times s plus 1 is 2 times 0 plus 1 is 1.
So you have a singlet multiplicity.
We call that a singlet. Let's take that exact same pair of electrons, one up and one down. What if you uncoupled them and now they're both pointing up, but they're in 2 different orbitals? So now 2 times 1/2 each plus 1 is 2 plus 1 is 3. Hence why we call this a triplet state. Basically, it just means, are you forcing them to be paired up and therefore opposite spin, or are you allowing them to unpin? That's going to be important when we get to the details of fluorescence versus phosphorescence.
Yep, and this can go pretty high. Right when you get into the D and the F orbitals, you can get quartets, quintets.
Oh yeah, it doesn't have to stop at triplet, right?
Mm-hmm. And generally, the higher the multiplicity, you'll get higher stability in some sense because you have a lower energy of the system when you have these unpaired that are occupying their own. And this leads us to the important concept and often mispronounced Yablonsky diagram.
I can't handle it. Is that seriously how you say it? I've been saying this wrong for 42 years.
Yep.
I've been calling it Jablonsky like an idiot. It's Yablonsky.
Yablonsky.
Get out of town. Is it Polish?
Yep.
Our listeners may not know this, but Andrew's a big fan of Poland.
Yeah, over COVID, if you see my last name, it makes sense. Over COVID, I attempted to learn Polish, and I found out there aren't too many Polish people here in Salt Lake, and most of the time, whenever you try to speak Polish with someone, they just revert to English pretty instantaneously. So it was a failed effort, but I learned how to pronounce everything, and I still retain quite a bit.
So these Yablonsky diagrams, what on earth are they? I see energy on one axis. I see a bunch of different energy levels. What am I looking at?
Yeah, if you're not driving, it would be very helpful if you can do a quick internet search to pull up one of these, at least a basic one. It'll make a lot more sense, or you could go to our Instagram page and you can check out the artwork for this podcast, which will also feature a Yablonsky diagram. Effectively, this is a schematic showing different potential energy states that an electron can occupy. You have electronic states. These are kind of your macro ones. These correspond to the principal quantum number. These will be S0 for the ground state, S1, S2, S3 for singlets. And within these, you have sublevels corresponding to vibrational or rotational energy modes.
Yeah, I had to Google this morning. I was kind of surprised to learn that. Basically, as the atoms are vibrating, it's opening up different energy levels where the electron could occupy, basically. So if things were absolute zero, it would just be a discrete single setting, but we're not at absolute zero. There is some amount of variability. And so there's a little bit of blurriness. There's additional levels that you can occupy with energy when you excite something from its lowest state up to these temporary higher states.
Yep. And as you get higher, all of a sudden the gap in the distinction between these states starts to become a little bit fuzzier too. They start to overlap. So for example, if you're in the highest vibrational state of the S3 electronic state, it starts to overlap with the lowest vibrational state of the S4 electronic
it's a band. We're forming bands. Okay.
Yep. And so that's for the singlets. You'll also get the same thing for triplets, although they're in a bit of a higher energy state.
Okay. So that's probably not shocking to anybody who listens, to this. They're probably familiar with the idea of energy levels and that things can be promoted. Where it gets interesting is the details of how things get promoted, and more importantly, how they come back down. That's where we get the light coming off these things that we can see. So there's different pathways. For one, we should introduce this concept of vibrational relaxation, right? So we said that as these atoms are vibrating, bending, all the different vibrational modes that can exist, that can allow it to slowly relax from the top of its band of excitation down to the lower band, as it gives, basically it's going to give off energy in the form of heat, right? It's going to allow the material to heat up, and it's going to slightly relax down to its lowest band.
Yep, vibrational relaxation will allow it to reduce its energy within an electronic state.
So we're still in an excited state. We're not back down to the ground, but we're going to lower itself to the lowest level of the excited state.
Within an electronic state. So if it's in, let's say, S2V5, vibrational relaxation can allow it to go to S2V1.
Yes, gotcha. And this is fast. This happens pretty quickly?
Very quickly, which means it's more probable.
Okay, makes sense.
But that's not the only way. There's also a process known as internal conversion.
Tell me about that.
We mentioned that as we get higher in energy, these electronic states start to overlap. And through the internal conversion process, one can go from, let's say, an S4V2 to an S3V5.
Because they're at comparable energy levels.
Yes.
Okay.
And so that's a
So
way
why-
where you
why
can
would they
shift
do that?
from a higher electronic state to a lower electronic state through a non-radiative process.
Is this like just a degeneracy argument? What's driving this?
A desire to reduce energy. Thermodynamics.
Always. Always is the right answer. Okay, so it's possible for them to switch between quantum numbers because these energy levels are overlapping. Okay, that's internal conversion.
Yep. And so by both of these processes, typically an electron can fall from higher energy states down quite a bit. But once it gets to the S1, right, that first energy level above the ground state, you start to get a bit of a gap. And that gap's large enough such that internal conversion and vibrational relaxation start to become a lot slower and less probable, and instead, you can get fluorescence.
So fluorescence then becomes a direct emission that occurs from dropping from this excited state directly down to one of your lower states. If you're familiar with like LEDs, and we haven't done an episode on this, but we should, when you drop from your conduction band down to your valence band, crossing the band gap, it gives off a very specific light. If you want a blue LED, right, then you know exactly what that energy difference should be. Well, that's essentially what's happening here, but at an individual atom level.
Right. But it's not necessarily going to always be the exact same wavelength either. Because even in the ground state, there are various vibrational states, so you can drop to one of those. So you actually end up with a spectrum.
Yeah, it's fairly tight. And maybe you've seen this before. In fact, if you have a glow-in-the-dark material, you can try exciting it. Try exciting it with like a red laser, and try it with a green laser. Try it with a UV lamp. And what you'll notice is that the phosphor or the fluorescent material is going to glow the same regardless, as long as whatever you're using to excite it has enough energy to promote it to that excited level. For example, a red laser doesn't have a lot of energy. It may not be able to excite your fluorescing material, your phosphorescent material. But what you'll find is if it is able to excite it, it's always going to glow essentially the same color. Now that process is slow. It happens something on the order of like a billionth of a second. But you compare that to like vibrational relaxtions, which were less than like 100th of a femtosecond. So this is a million times slower, ballpark. What does that mean in terms of likelihood? It means that it's less likely.
Yeah, this observation that regardless of what energy you use to excite it, it tends to emit within a certain range of wavelengths is actually characteristic, right? Typically, you're not going to receive the same amount of energy you put in because of those non-radiative processes. That's where your energy
That's the
is being
heat loss,
lost.
basically.
And you can characterize this with the Stokes shift, which is the difference between the maximum absorption spectrum and the maximum emission spectrum.
I gotcha. So in terms of if you want like a high-performing phosphor, this is essentially going to give you information about what often gets called the quantum efficiency, right?
Mm-hmm.
Photons in versus photons out.
Yep. Now that describes fluorescence, but to get to phosphorescence, it's a slightly different mechanism. Rather than descending down the singlet electron configurations, we have to do something called intersystem crossing, where an electron can actually change spin multiplicity going from an excited singlet to an excited triplet state.
So back up and remind me how this works. Remember, we said that a singlet is when you had one electron up, one electron down, no net spin. And a triplet is when you had things now both pointing the same direction. So what has to happen for phosphorescence to occur in this intersystem crossing is that you essentially have your electron switching from up to down, down to up, right? It's switching its spin, and that changes the multiplicity, and it ultimately leads to phosphorescence.
Yeah, this is termed a forbidden transition, actually, because it's not supposed to be able to occur, but due to weak vibrational coupling, it can. And if you look at a Yablonsky diagram, you'll see that the triplet states are, in some cases, just a bit lower than various singlet states, so it represents a viable path to reducing energy, although it's very slow and much less probable most of the time.
Now, the slowness of it we can actually use to our advantage, right? The reason when I started this episode saying that those sort of colored stars on your ceiling don't glow for very long, but things like some ceramic materials can glow for a really long time, is exactly because it is a phosphorescent material where there's a time constant, which is you're basically trapping the photon there for longer than it would like to be.
Yep, and when it eventually does decay from that triplet state back down to the ground singlet state, that's your new emission. But note that's also going to be a much longer wavelength, lower energy than the fluorescence.
Yep. Okay. One last thing that we should introduce before we start talking about some materials is this notion then of a luminescence lifetime. We just kind of mentioned it. It's essentially the average time that a molecule or a material remains in its excited state before returning to the ground state. Does this happen over a matter of seconds, minutes, hours, right? And there's actually materials that sort of do all the above.
And with that, why don't we move on to some fluorescent materials, often a bit more complicated than the phosphorescent materials.
Way more.
There's tons of different mechanisms. I was kind of shocked. I thought I was hopeful I would find a nice little review article.
No,
but
dude, it's messy.
It's very diffuse and there's lots of nuance, but we can cover a couple of the big main types that you'll see. So just as a recap, fluorescence is a prompt emission. So you put light in and you're going to get light out, and it's not going to last particularly long.
Yeah, think of like I'm here in Utah. Maybe we'll post this on the Instagram story, but I love to go hunting for scorpions, right? And it's really fun to take a black light, a UV light, and you can, holy cow, at night, these scorpions, which you cannot see otherwise, show up super bright, like a bright, bright green. But the second you turn that light off, it's over. This is fluorescence. It's not phosphorescence.
Yep. And these can take the form of polymers, quantum materials, or inorganics. Maybe we can start with polymers. These are typically going to be what are known as conjugated polymers. These contain lots of alternating single and multiple bonds, which enable the pi electrons to become delocalized, creating a little bit more of a diffuse.
Yeah, I remember the first time I learned this, it seemed I didn't quite get that. So the reason why it needs to be an alternating single, double, or something, like acetylene is a classic example here, is because of hybridization, right? When you form a double bond, it's a different... Carbon still wants to have 4 bonds, but it changes the shapes of the orbital. The hybridization changes. And in an alternating scenario, what you have is your p orbital sticking up for every single one, basically. And because they're sticking up and they overlap, this becomes a band. This is a way where you can actually have conductivity. So that becomes an important part of forming what chemists call your HOMO and LUMO bands, the highest occupied molecular orbital and your lowest unoccupied molecular orbital. What we as typical material scientists call your conduction band and your valence band. It's the exact same thing, but in a molecule.
Yep, and this conjugation is key to reducing that gap, such that UV photons, for example, or light photons will have sufficient energy to cross it.
Yeah, if it was too big of a gap, then UV light wouldn't be enough to excite it. Okay.
Yep, and so a lot of times you'll see, like we said, alternating bonds, which when you think of that, you might think of ring structures.
Benzene, right? Benzene does this.
And the length of that system also affects the energy gap.
Right.
So the longer that is, the smaller that gap is going to become, which is going to change the light emitting properties too.
Now you can modify it though, right? That's like your starting point. Is the template is to have this alternating single, double. But then you can swap things out, and this is how you get the introduction of sort of trapped states, for example. You can introduce groups like NH2 groups or OH groups. These are going to be electron donors, but you could also have electron accepting groups like an NO2 group or a CN group, right? Sometimes called this oxochromic groups. These are going to modify essentially the available spots for an electron to get excited into. So we can think of them as dopants basically in a semiconductor system.
Yeah, but they both behave in a very similar way. They both effectively narrow the gap. They just do it in a different way. So donors raise...
Coming from the bottom up or the top down.
Yeah. Donors raise the HOMO energy, while acceptors lower the LUMO energy.
Okay, so we can move the energy gap with these donors or acceptors. But before, we also talked about vibrational relaxation, which is when, okay, you excited it, it can still sort of move up and down within that excited state if there are vibrations. And not all polymers are equally, rigid. Some are going to be more and some are going to be less.
Yeah, and it turns out for designing highly fluorescent molecules, we want these to be more rigid to reduce the chance of non-radiative emission.
Yeah, you don't want it turning into heat. You want it to force to come back out as light.
Yep.
Okay.
So many of these come in the form of dye molecules, collectively somewhat referred to as fluorophores. So these are things like rhodamine, fluorescein, coumarins, and cyanines.
Actually, one of the students in our research group, Lucas, he's working on a project where he's trying to make a super easily cleanable surface, like for biomedical applications. You don't want things to stay dirty. And it's really cool. One of the tests that is like the ASTM standard for measuring this is they take vitamin B, which fluoresces, therefore you can see it very easily. They'll stain the surface with this vitamin B solution, they'll clean it, and then they'll hit it with the UV light, and they can see what fraction of it is left over, which is super cool.
Oh, that's kind of like when you ever went to the dentist and they made you eat those tablets that would coat your teeth, and then they'd make you brush, and they'd look at it.
Same thing, but using fluorescence here.
think it's fluorescent for them too.
Oh, do they as well?
It might be a chemical reaction.
He just made me walk around with a big red smile all day.
But some of the advantages of the polymers is you can get pretty good high quantum yields. And as with most polymer things, you have a massive design space. So depending on what sort of fluorescence you're looking
the benefit
for,
of molecules, right?
you have a lot of flexibility. But they suffer from various issues like photo bleaching, where you're exciting electrons into higher states. All of a sudden, new chemical reactions can take place that will result in degradation.
You can break bonds, right?
Yeah.
We were relying on this sort of bond architecture to create our homo-lumo gap. But what if you hit it with something so strong that it actually breaks bonds, right? Now all bets are off.
Yeah, this happens pretty often with polymers when you expose them to UV light. You get yellowing and various degradation. They're also super sensitive to the solvent environment that they're placed within. So you have to be very careful about various environmental factors.
Yeah, and just think of like if you've ever highlighted a paper, I don't know if you guys are still reading in paper Gen Alpha, all right? But if you've ever highlighted it and then you come back to that a couple years later, it doesn't glow like it once did, right? These things they're a little less stable long term, right? They're not as stable as, say, phosphors.
That's one category. The next one that's also very important are quantum dots. These are nanoscale semiconductor crystals.
Typically inorganic materials.
Yes, and they become fluorescent due to quantum confinement, where just how
totally different mechanism.
few atoms there are naturally results in very discrete energy levels that are very controlled. And depending on the size of your quantum dot, you can directly tune that band gap.
Yep. This was the Nobel Prize, right? 2023. It was exactly for this observation that by tuning the size of these things, you tune the band gap and you get different colors. And if you've seen pictures of really bright solutions doing like the rainbow color, it might well have been quantum dot. These things are really impressive. They've got lots of applications in tags and markings, very, very cool stuff.
Yeah, and even in displays too. They have advertising all these. But you know what's interesting that I didn't quite realize is that behind these quantum dot displays, they're still hitting them with blue LED light.
Yeah, and they got to excite it still.
Yep.
Yeah, I'm not surprised about that. It's cool though.
And so typical materials here, typically these are in a core shell configuration. So your core will be something like cadmium selenide, cadmium sulfide, indium phosphate. But because these are so small, you have tons of dangling bonds on the outside, and these can vibrate. And so that opens a lot of pathways to non-radiative energy dissipation. So you'll typically passivate them with a high band gap semiconductor material.
Why? I assumed it was to prevent sort of aggregation and coarsening over time, which you could learn about when you learn about ceramics, right? They have a whole course on coarsening. But it's about the vibration modes on the surfaces, you're saying?
It might be a little bit of both. So when I was looking at the literature, it'll typically have several layers, but you'll see something like zinc sulfide, where its high band gap will just basically make it so the electrons don't want to transfer over there.
Yeah, that makes sense. Very cool. Okay.
There's also fluorescent proteins. These are becoming very important in various biomedical applications. We're probably not going to talk too much about those.
Beyond the scope of this work?
Yes.
We will come back to them. If you guys want it enough, we will come back to proteins that glow. Then you've also got your bulk inorganic materials and minerals, right? So, and again, we're moving away from the organic materials. In the world of inorganics, you can have lots of fluorescence. In fact, if I could throw out one of my favorite places, if you ever find yourself in Golden, Colorado, they have a mineral museum. And down in the basement of the mineral museum, they have a little fake cave. And in the fake cave, they have all the glowing rocks. And it is amazing. Absolutely amazing. Now, not all minerals fluoresce, right? But you've got here the stat says about 15% of minerals fluoresce, which is amazing. Makes me want to bring my black light with me out on my hikes.
Yeah, I bet you could find tons of calcite on there, which is a common fluorescing mineral.
I've got a big block on my desk at work.
And what's interesting is that what's causing the fluorescence is not the calcite itself, but what's in the calcite.
It's the dopants, right? It's the impurities.
Yep, it's what they call activators, because a calcite sample from New Mexico will fluoresce very different from a calcite sample in Utah, for example,
that's so
depending
cool.
on
you could use that
chemistry.
for like provenance tracking, right? Figuring out where something's from is if it has what impurities it had present in it.
Yeah, I'm pretty sure they do this in nuclear deterrence analysis.
I know they do, right? Super cool.
But
so how's it working? What's it actually doing?
Yeah, so for a very simple example, a common one, let's assume we have manganese. It's divalent activated calcite. So the manganese can swap for the calcium because that's also 2+.
Yep.
And this leads to the introduction of new electronic states within the band gap of calcite.
Okay.
So in free manganese, you have 5d orbitals. These all have the same energy. We call them degenerate. But when the ion is placed within the calcite crystal lattice, the surrounding oxygen atoms create an electric field, which is termed a crystal field, and this causes the d orbitals of manganese to split into a bunch of different energy levels. And this breaks the original degeneracy through what they call crystal field splitting, but now you end up with discrete energy states.
2 above, 3 below. This takes me back to my PhD dissertation. Did all of this in my PhD. Yeah, very cool. And it's typically pretty small. That crystal field splitting is rarely very large. We're not talking like band gap level big. It could be, fractions of an electron volt, but it's a difference.
And it's enough. And it's actually the combination of these, that rigid ordered calcite crystal actually enhances the fluorescence of manganese, which on its own wouldn't fluoresce.
Cool. But it's critical for providing that rigidity to prevent the vibrational relaxations then.
Yep, and it's really sensitive too. Small changes in that coordination environment can totally change the crystal field splitting and cause different colors to fluoresce. What's also interesting is too high of an activator concentration, the fluorescence behavior disappears.
No way, that's wild.
Or the presence of other dopants, things like quenchers, which can reduce fluorescence by opening additional non-radiative pathways.
Okay.
And these can get pretty complicated, so we'll probably leave that to maybe a future episode. But manganese in concentrations up to several percent can even cause different fluorescence depending on the minerals. Like we said, that different coordination environment. So you'll get red or orange fluorescence in calcite, green fluorescence in willemite, yellow fluorescence in esperite, and orange fluorescence in wollastonite.
So you see basically the color spectrum from the same activator, manganese, in different environments.
Mm-hmm.
Because of different crystal field splitting, because of different stresses on it and sort of rigidity.
Yep.
Cool.
And it's not just manganese. You'll also have lead, uranil, which is uranium oxide, europium, yttrium, samarium, chromium. There's a variety of examples.
Yeah, if you've ever seen ceramic pottery that has a uranium glaze on it, hit that with a light and you'll see it. That's exactly one of these.
Yep, but don't eat from it.
I think they supposedly put a glass on it that should lock it up, but I would always be super skeptical myself on that.
It's a nice piece to put up somewhere, and it's totally safe. If you
just don't eat it.
Just don't eat it. These are the materials, as we mentioned at the beginning, that you'll typically find in fluorescent lights. So these have gone through several iterations, but you'll typically see things like barium manganese aluminate with europium being doped in there, yttrium oxide with some europium in there, and these will be combined, like we had mentioned, to achieve lots of different wavelengths. And these fluorescent materials find applications in bioimaging, sensing, lighting and displays, various security inks, and tagging, and even some solar concentrators.
Oh, cool.
I think if you recall from our cooling paint episode, we mentioned that titanium oxide is susceptible to fouling when it's being exposed to high UV radiation. And so a mitigation strategy is to include fluorescent materials that will absorb the high UV and will actually re-emit it in a wavelength that the titanium
can use without fouling.
Yep.
Oh, that's cool. That's a way cool application. All right, so we've covered at least some of the common fluorescent materials that are out there. Now, what about phosphorescent materials? They're very, very similar. Now, like before, you have your host material, and you're still going to have to dope it, as it were, with something in order to get these elevated states, the ones that you're interested in, that you're going to get light from as it falls down from them, right? These are still going to be called our activators, but now we're also going to have what are called sensitizers, and these create trapped states. We're going to try and trap these electrons, because the key difference, at least in one of my viewpoints of these two different approaches, fluorescence versus phosphorescence, is how much longer phosphorescent lasts, and you get that by trapping these things in place.
Yeah, through the introduction of these trap states, you can prolong the lifetime of electrons, such that in these trap states, they're deep enough to prevent it from just sort of spontaneously making its way out, but not so much that through just room temperature, through a thermally activated process, these electrons can slowly work their way out of these trap states and then eventually fall down and emit light. And so by controlling the extent and the depth of these trap states, you can prolong the lifetime. And that's how you can get phosphorescent materials that last on the order of hours.
Yeah, actually, the roadway paint that we do, we have it on a bunch of bike paths here in Salt Lake City. By the way, JCS Labs, if you're interested, we would be happy to come paint some stuff for you. I'll put it in the show notes. But we actually painted it, and then we illuminated it with UV light, and we came back in the morning by 6 a.m. It was still technically glowing a little bit. You could still see it. If you don't illuminate with the UV light and you just let the sun do its thing, it glows until the early morning hours, which is wild.
Mm-hmm. And some other common materials will include zinc sulfide. They typically dope this with copper. These are all really cheap. This is what you find in those stars or various kids' toys.
Yeah, I mean, copper's not expensive. Zinc's definitely not expensive.
And copper also creates these trap states, but they're not as deep. They don't last as long. As you mentioned, the strontium aluminate with europium and dysprosium, that's like the high-performing one.
You pay for it, though. That's the stuff that we use. It's a little bit more expensive, but it lasts way longer. And there's other materials. There's calcium sulfide. You can dope with bismuth. In these phosphors, there's actually a range of different colors you can get. There's even like some red ones. There's lots of blues and greens that you can commercially buy today.
But these can be challenging to process, but polymers just really don't do it. They aren't able to create deep enough trap states, and the availability of other vibrational modes or other means of non-radiative
You just get vibrational
emission.
relaxation. Yeah.
Yep. But people have tried, and that's where you've gotten these crazy things, these metal organic complexes where you are taking things like iridium, platinum, ruthenium, osmium, and you're attaching various organic ligands.
I didn't know about these. When you found this, I was looking through your show notes ahead of time. I was really surprised about these. So yeah, you take these expensive, unfortunately, platinum group, mostly metals, and then you surround it with like organic ligands, and then the benefit here is you can really control. First off, you're getting the excited states from the metal, but because you can attach with ligands, you have lots of control over the vibrational relaxations and all these different pathways. So you get huge tunability in the colors that can come out of these things, right? Because there's all sorts of different ligands that you could choose. So incredible flexibility here, and really, really high quantum yields, like almost 100%, right?
Yeah, but they're expensive. You pay for them as well.
Iridium,
but you can,
platinum.
Yeah, you can do it through solution processing, which opens up cheaper processing routes.
Man, if you could find a metal that to sit in the middle of this complex that wasn't one of the expensive ones that gave you the same flexibilities, now you'd be dealing with something really pretty game-changing. Okay, clearly ceramics are awesome. I'm obviously a fan, and we are a fan of them because the American Ceramic Society has been a sponsor of our show for a long time. And if they can do phosphorescence, what else can they do? We want you to learn more of what they can do by checking out the Acers Learning Center.
Yeah, whether you're new to the world of ceramics or a seasoned professional, there's always something new to learn in their on-demand courses. From things like the Introduction to Ceramic Science to the Introduction to Advanced Ceramics, the Acers Learning Center helps you set the foundation with fundamental knowledge. So you can visit ceramics.org/materialism, and you can use the code materialism to get $100 off your next on-demand course registration.
Can't beat it.
The Materialism podcast is also sponsored by Materials Today. You can visit materialstoday.com to stay up to date on the latest happenings in the material science field and read some of the fantastic articles that they've published. You can also head over to elsevier.com to find out more about their journals, books, conferences, and related programs.
And as always, we are so excited to have you guys a part of the show. I just got back from a conference where I met with so many listeners. It is absolutely unreal to be connecting with audience members from around the world. We would love, love, love to hear more feedback on what stuff you guys want to hear. You can find us at materialism.podcast@gmail.com or the @materialismpodcast on Instagram, or pretty much everywhere you want to find us. We are out there, and we love hearing feedback on the show. Special thanks to the people who make the music possible for this show, Alphabot and Kolobyte. We appreciate you. And that's it. We will see you guys next time.
The inventors of fire, electricity, magnetism, iron, lead, glass, silk, cotton, the makers of tools, the captors of lightning, the architect, the engineer, the musician, are all beneficiaries of the materials of this world and are bound only by their imaginations in manipulating those materials.